Okay, we are going to continue with the problem of rotating charge distributions. So let me just write rotating the title. But now we're going to do it, solve the problem from a different angle by using Fourier transform. Okay, so let me read the text again. So the next part of the problem is to use the Fourier transform technique. So basically, what we're going to say is that we have a charge distribution which rotates with a certain period, which oscillates with a certain period. Okay, so we consider a charge density. So this is part B of the problem, and we consider a charge density rho xt. Okay, and it rotates with a period of 2 pi divided by omega 0. Okay, and we want to make a Fourier series expansion of this and relate it to the previous results that we had. Okay, so we want to show how this is written in a Fourier expansion. And of course, you know that if you have this period, what should happen is that rho xt is going to be given by a time-independent term plus a sum over n rho n x e to the I n minus I n omega 0 t. Okay, and here, of course, rho n of x is given by 1 over t 0 to t dt rho x t e to the I n omega 0 t. Okay, so that's our that's our Fourier component. Okay, and but what we want to actually write is not this. This is obvious. We want to take the real part. Okay, and you know that in order to take the real part, if rho xt is to be real, and it's a charge density, so it better be, then we have this identity. Okay, so if we switch n, the Fourier index, the discrete Fourier index n, if you switch the sign of that, that should complex conjugate, and indeed it does, right? So if this number is real, then if I complex conjugate this, that's the same thing as switching the sign of n. Okay, and we're going to use this to rewrite rho xt in a different form. Okay, so I have my rho, sorry, let me actually start that again. I have my rho xt, which is rho 0 of x plus, well, I should have actually indicated one thing, sorry, that here there's no 0 term, but there are plus and minus terms. Okay, but what I'm going to do now is I'm going to write only rho n plus n greater than 0 indices. In other words, I can write rho n x e to the minus I n omega 0 times t, and plus, I could write here rho minus nx, okay, but I'm going to use the identity. I'm going to write rho n complex conjugate x e to the I n omega 0 t, okay? So basically, we can rewrite this as rho n x plus n greater than 0, 2 times the real part of rho n x e to the minus I n omega 0 t. Okay, so that's the, and this is actually remarkably similar to what we found in the previous problem, or in the first part of the problem. So we have rho 0 that doesn't radiate anyway, but we have 2 times the real part of a complex number. Okay, and we had the same thing here. This is a 2. Okay, so 2 times the real part of this rather involved complex number. Okay, so that's part B of the problem, and let me now do part C. Okay, in part C, we're going to analyze one single charge rotating. Okay, so in part C, what you want to do is to um, so take a single charge rotating about the origin in the xy plane. Okay, so single charge Q, and it rotates on the xy plane. Okay, and we want to calculate the multiple moments. Actually, it asks for L equals 0, L equals 1, but what I will do is actually give the generic expression. And but the main part is to compare parts A and B of the problem. Okay, so I have a charge density, okay, of a single charge rotating about the xy plane. So that's going to be qr squared delta r minus r delta cosine theta delta, and here I'm going to have phi minus omega 0 t. That's my charge density. Okay, so that's my starting point for solving the problem. Um, and the first thing we can do is to calculate the time-dependent moments of this quantity. So QLMT is going to be, well, triple integral r prime squared dr prime sine theta prime d theta prime d phi prime. Then I'm going to have an r prime L and a YLM star theta prime phi prime. I will leave this here because I'm going to shift the phi variable as I did before. Okay, so let me actually do that already. Okay, so I'm going to already shift the phi variable. So now, since I already shifted it here, I have to shift this one too. Well, that's going to, and so I still have to write in the charge density, of course. So Q over R squared, the constant, I brought it out in front of the integral. And I'm going to have here R prime minus R delta cosine theta prime and delta phi prime. Okay, delta phi prime. Yeah. So actually, what this does, we can easily integrate this. We didn't need to shift it actually. It's just as easy either way. But we can, first of all, we can easily integrate this the dr prime integral, right? The dr prime is just a delta function, so it gives us a capital R wherever we see an r prime. We can also integrate this delta function, but we have to need a, well, strictly speaking, we need a variable transformation. So we're going to set x equals cosine theta prime, which means that we have a dx, which is minus sine theta prime d theta prime, which also means that the limits go, which used to go from 0 to pi in theta prime, now go from -1 to +1, okay? But basically, where this is actually going to pick up the contribution where x is 0, i.e. where cosine theta prime is 0, and cosine theta prime is 0 when theta prime is pi over 2. Okay? And integrating d phi prime just gives us a phi prime equals 0. Okay, so when we do all that, what we're going to get is q r to the to L, because we got an r prime L plus 2 that gives us an r capital R to the L plus 2, and is divided by r squared. Okay, and then we're going to have here YLM star pi over 2, and here I'm going to have an omega 0 t as the argument because I made phi prime equals 0. Actually, I don't want that. What I'm going to write instead is a 0 here and an e to the minus I m omega 0 t out here. That's equivalent, okay? So this is actually our time-dependent moment, okay, when we take the charge density. Sorry, I forgot to say that the charge is rotating at a radius, capital R, in the xy plane. So it's rotating at a radius, fixed radius of capital R. Okay, so that's actually our time-dependent moment for a single rotating charge. Now we want to do, based on this, now we want to compare this to the Fourier scheme. Okay, so what I'm going to do is calculate a rho n x first. Okay, and if I calculate a rho n x, well, that's going to be 1 over t, 0 to t, dt. And here I have to write the charge density, q over r squared, delta r minus r, delta cosine theta. And then I have delta phi minus omega 0 t and e to the minus I n omega 0 t. Okay, so that's my integral. I think the easiest way to deal with it is to introduce a new variable. Let's call it tau, which is omega 0 t. Okay, and if you do that, what you're going to get is rho n x. So so basically what's going to happen if you switch to this variable tau omega 0 t, okay, then, well, okay, let me write this explicitly. So your integral is going to be, so I can write here 1 over omega 0 t, 0 to omega 0 t, and omega 0 t is actually 2 pi, so I could actually already make this a 2 pi, so d tau, and I have q over r squared, delta r minus r, delta cosine theta. These guys for now just go along for the ride, but now we have delta phi minus tau e to the minus I n omega 0 t, sorry, omega I n tau. Okay, and basically what you're going to get for an Rnx, obviously, is 1 over 2 pi q over r squared delta r minus big R delta cosine theta. And this delta function, what it gives us, so for the mess I made here, is e to the minus I n phi. Okay, so this is our Fourier mode. Okay, this is our Fourier mode. And then what I'm going to do is write this Fourier mode as a as a moment, as a multiple moment. Okay, and then see that how it relates to the other multiple moment that we found. So I'm going to call this multiple moment NLM, say. Okay, and well, it's we don't need to worry about the time dependence, okay, because the time dependence is in the, well, when you write the Fourier, this is the this is the n dependent part, so this doesn't have to have a time dependence. The time dependence is taken care of when you write the full rho xt with the help of this Fourier series. But what I can do, so I will keep this time independent and see what happens. So I have, I'm going to have, well, triple integral, okay, and r prime squared dr prime sine theta prime d theta prime d phi prime. What else do I have? I am going to have an r prime to the L. I'm going to have YLM star theta prime phi prime. And now comes the charge density, or actually not the charge density, but what we found, the Fourier mode of the charge density, which is, so all of these are multiplied. Okay, and now I'm going to multiply by Q over 2 pi r squared, delta r minus r, what we found, delta cosine theta, this is primed, and I have an e to the minus I n phi prime here, okay? And, well, we already know what the r prime integral does because it's a delta function. We already worked out what the the theta prime integral does. So let's actually just quickly get that out of the way. So I'm going to pull out the q 2 pi r squared, And what I'm going to have here, sorry, this r squared is not here, it's r to the L because of that part of the integral. And then I'm going to have y L m star pi over 2, but I keep this phi prime here because I haven't done it yet. I n phi prime. And here we still have the phi prime integral to deal with. Okay, and now the important thing here is that if I want to integrate this phi prime, right? I want to integrate this phi prime, and I know that the spherical harmonic actually has a particular phi dependence. Okay, and that's actually I seem to have made a mistake. Sorry, and I will fix it. It's not hard. This should have been a plus. Okay, so this should have been a plus all along. This should have been a plus. So this is also a plus, and this is also a plus. Sorry about that. Okay, but basically this y lm star phi prime, we can extract the phi prime dependence, right? So the phi prime dependence is e to the minus I m phi prime of the spherical harmonic. What you're going to have it is an e to the I n phi prime d phi prime integral, and if I divide it by 2 pi, I use this 2 pi that was here, this is actually a delta function. This is none other than a delta function. So basically our time-dependent moment in this case is going to be q r to the L, and I can, since I basically I took out the exponential e to the I m phi prime of the spherical harmonic. Okay, so I can put a 0 there. Okay, so basically the rest of the story is that, okay, so I have this delta mn here and y l m star pi over 2 0. Okay, so the only difference, it seems, is this delta mn, but we see that that actually makes the Fourier, so basically of the Fourier modes, it extracts the correct mode for a particular, so this delta function will extract the correct mode for a particular for a particular multiple moment. Okay, so so these two are actually consistent. That's what we have shown. Okay, thank you very much. This is the first problem.